Hello. So lately I made a foray into differential geometry. And yesterday I decided to make a video about what I grasped so far. So I came up with this title, Curvature Tensor and the Covariant Derivative. I don't know how consistent this title is, but I just found that the curvature tensor and the covariant derivative are very related to each other, so you can understand one of them in terms of the other, and vice versa. This guy is of course Christoffel, and this guy needs no introduction. He's Riemann. I decided to slap these photos here just to sex up the video. Now, of course, what you see on the left is the setup of our problem. So we've got a three-dimensional ambient space, and embedded in that space is a two-dimensional curved surface parameterized by S1 and S2. And hopefully we're going to extract covariant derivative in the way of deriving the curvature for this surface. Now, before we begin, I just want to make a very important distinction here between the bases that get changed from one point to the other due to the nature of the coordinate system that you chose, and the bases that get changed from one point to the other due to the curvature of space. To understand this difference, assume we have a Euclidean space, say two-dimensional, and in that space we decided to deploy the polar coordinate system. Now, the polar coordinate system is quote-unquote notorious for its variable bases. For example, at this point, these two vectors represent the bases, while if you move over to this point, these two vectors are the new bases. Now, the way to capture this rate of change is via using the Christoffel symbol gamma kij, which is simply defined as the rate of change of each of the covariant bases with respect to each of the spatial variables dotted with each of the contravariant vectors in order to produce the contravariant components so that we can later combine them with the covariant bases in order to reconstruct the rate of change. So the Christoffel symbol is not just simply about finding the rate of change of the covariant bases, but it's also about decomposing the resulting vector in terms of the covariant bases themselves. That's why we did a dot product with the contravariant bases. And the resulting components will be captured by this symbol. So in case you have a three-dimensional space, we're talking about 27 components. And if you're not very sure about this covariant-contravariant thing, I'll make a video about it later on. For now, I need you to keep in mind that if the Christoffel symbol is equal to 0, it means we have a Cartesian coordinate system or any other system in which the bases don't get changed from one point to the other. If the Christoffel symbol is not equal to 0, it means we have some coordinate system with variable bases. Now at this point, we need to understand a very quintessential fact, which is that this equation only holds because we don't have a curved space. What this equation really saying is that the resulting vector from differentiation process can be fully expressed in terms of the basis of the point that we started with. For example, assume we started with this point and we want to find the rate of change of the basis as we move from this point to an adjacent point. So we have to subtract these bases from the new bases. And the resulting vector from this subtraction can be fully expressed in terms of these bases of the point that we started with. That's what this equation is really saying, and it only holds because we don't have a curved space. Okay, now let me define a new function, and bear with me, let me just call it the covariant derivative. Okay, let's put that as J, covariant derivative of the covariant bases Zi. And this new function simply equals this guy minus this guy. So that will be dou Zi by dou Zj minus gamma Kij Zk. And because this guy equals this guy, and we're subtracting those two here, that means that the covariant derivative of the covariant basis is equal to 0 in case we have a Euclidean space. And if we have a curved space, this guy won't be equal to this guy, and thus the resulting subtraction won't be 0. In fact, it will be something that indicates how much curvature you have. So let's just keep this in mind. If the covariant derivative of a covariant basis is equal to 0, it means there is no curvature. Let's just say that's a Euclidean space. Okay? And if the covariant derivative of the covariant basis is not equal to 0, it means we have a curvature. Okay, now the question is, how can this term be different from this term? Well, that's what we're going to answer when we examine this problem. Now, I'm pretty confident that you still remember this surface. It was parameterized by S1 and S2, and let's just make sure that we are on the same page. This is constant S1 line, this is constant S2 line. Okay, and this is the grid imposed on this surface when it was parameterized by S1 and S2. Now, of course, the rate of change of the position vector when parameterized by S1 and S2 with respect to each of the spatial variables will result in the covariant basis. When I say the covariant basis, I mean those two vectors. You see them, S1 and S2. So those are the covariant bases. They are intrinsic to the surface, and they are different from the covariant basis of the ambient space, that is Zi. Now let me remind you that those covariant bases keep changing from one point to the other. So at this point we have S1 and S2. If you move to this point, we have different bases. If you move to this point, you have different bases. And let me just remind you that at each point, those two basis vectors define a plane that is tangent to the surface at this point. And by the way, I have a graphical example that tells you what I mean. There it is. So the blue thing is the surface, and the pinkish plane is the tangent plane to the surface at the point P. And what do you need to define a plane? Well, it is simple. You just need two basis vectors. And we do have those two basis vectors already. Remember, we just differentiated the position vector with respect to each of the spatial variables, and we got S alpha, that is S1 and S2. So, in other words, we have got a plane tangent to the surface at each point. Okay, now I think we are more or less ready to find the covariant derivative of the covariant basis, S alpha, which is going to give us an indication of how much curvature do we have at a particular point. Now, don't get confused, because this equation is just the same as this one. Let me show you this one. Yes, I just renamed the indices. So instead of Z, I'm now using S, because, you know, Z is for the variables that belong to the ambient space, while S are for the variables that belong to the surface embedded in that space. And I also renamed the indices. So instead of using Latin indices like I and J and K, I'm now using Greek indices, alpha, beta, and gamma. So the Latin indices are for the ambient space, and the Greek indices are for the surface. So the Greek ones go from 1 to 2 because we just have a surface, while the Latin ones go from 1 to 3 because we have a three-dimensional ambient space. Okay, now we want to focus our attention on this equation, the covariant derivative of the covariant basis. Let's start with this term. It equals to the partial derivative of the covariant basis with respect to each of the spatial variables, that is S1 and S2. So assume we are at a particular point defined by S01 and S02. Okay, and at this point we have the covariant basis given by S1 and S2. And this is the plane that is spanned by those two basis vectors. Remember, this is the tangent plane to the surface at this point. And then we started to move from this point to this point. That is S01 plus delta S1. So we changed from S1 to S1 plus delta S1, and we kept S2 constant. S2, S2. In other words, we're trying to find dou S alpha by dou S1. Okay? And then as we moved from this point to this point, we trying to find the difference vector. You know, derivative is all about the difference. So we subtract S1 from S1 prime and S2 from S2 prime. So we get two difference vectors. And that's just because we moved from S01 to S01 plus delta S1. If we moved from this point to another point and changed S2 instead of S1, we will get another two set of vectors. So the total is 4. So when we're talking about this object is actually 4 vectors encoded inside this object. Alpha and beta change from 1 to 2. Each one of them change from 1 to 2. So we have 1, 1, 1, 2, 2, 1, 2, 2. So 4 vectors encoded in this object. But let's just focus on one of them. And all of the discussion applies in a straightforward manner to all of them. So let's just focus on this one, S2, and see how it changed as we moved from this point to this point. So it was S2, and then it became S2 prime. Now the difference vector will be pointing from the head of this one to the head of this one. Okay? And let me just denote this difference vector by this pen. Okay? So this pen is actually this object. Partial S alpha by partial S beta. So this guy is the partial derivative of the covariant basis. Actually one of them. There are actually 4. This one is just one of them. Now, what is strikingly noticeable about this resulting difference vector is that it doesn't belong to either one of those two planes defined by S1, S2, or S1 prime, S2 prime. It doesn't belong to this plane, and it doesn't belong to this plane. Sorry? Okay? In other words, you can't express this vector in terms of these spaces because it doesn't live in the plane that they span. Nor you can define this vector using those two basis vectors because this vector doesn't live in the plane that they span. Do you know what this implies? No? Well, let me tell you then. It means that this object is not equal to this object, which means that the result of subtraction will not be equal to 0, which means we've got a curvature. Yes, that's what it means. Because what you're trying to do in this object is representing this vector, which is this difference, in terms of the those two covariant bases, S1 and S2. That's what you're trying to do here. It's denoted by S gamma. Okay? But you would not be able to do this successfully because this object doesn't even belong to this space, to this plane, okay, to be more specific. So your attempt will be abortive. Hence, this would not equal to this. Your representation using S1 and S2 will not be a complete representation of this vector. Thus, a difference between those two will exist. Okay, so does it mean that it is false to calculate this object because you will not be fully and satisfactorily able to represent this vector? No, it does have a meaning to calculate this object. Working out this object entails bringing this difference vector, which is this, okay, and then dotting it with the contravariant version of these two bases, S1 and S2, in order to produce the contravariant components captured by the Christoffel symbol, that is gamma gamma alpha beta, and then combine these components with the appropriate covariant bases, that is S gamma, the same as S1 and S2, in order to produce the best possible representation of this vector using those two bases. So that's what it actually means to calculate this object. And geometrically speaking, this object represents the projection of this vector onto this plane. Now, do you know what it means to subtract the original vector, which is the pen, the difference vector, from its projection onto this plane? It means finding the orthogonal to this plane. I'll explain this. It's very simple in case you are familiar with the Gramschmidt orthogonalization process. It's very simple anyway. Assume we have a plane that is spanned by those two little vectors. And then we have a vector that belongs to a space outside this plane. And you want to represent this vector using those two basis vectors that span this plane. Then the best representation you're going to get is something like this, which is the projection of this vector onto this plane. And then if you try to subtract the original vector from its representation or projection onto this plane, then this is going to be the result. This is the difference vector, okay? This is the difference vector. The difference between the original vector and its projection onto this plane, and it is orthogonal or normal to this plane. Okay, so once again, when you subtract the original vector from its projection onto this plane, the result would be something orthogonal to this plane, so we can actually represent the answer, which is the covariant derivative of the covariant basis, by n, a unit normal vector, then scale it properly, and the scale is actually b alpha beta, where b alpha beta is the curvature tensor. I already told you that the difference is an indication of how much curvature we have. You know, when the result was 0, it meant that we had no curvature at all. We had a Euclidean space. Now, in case you don't believe that the result is actually normal to this plane, I've got a trick to convince you. Here is the same equation. The covariant derivative of covariant bases is the rate of change of the covariant bases with respect to each of the covariant, with respect to each of the spatial variables minus gamma gamma alpha beta is gamma. Let's multiply this dot product, both sides of the equation, with the contravariant basis. That is S gamma. This one with this one would be equal to 1. And here we have another S gamma dotted with this. And we have another S gamma dotted with this. Okay, S gamma dotted with this rate of change is equal to gamma, capital Gamma itself, you know, this gamma. So this will cancel out with this and the result would be 0. And what this actually means is that this vector is orthogonal to this. Remember, this is the contravariant basis, which span the same plane. The covariant and the contravariant bases both span the same plane. So it means that this vector is orthogonal to both of the spaces, both of the covariant bases, which means that it is orthogonal to the whole plane spanned by those two guys. Okay, so this is another proof that the result is actually the normal vector times some scalar values. So b alpha beta is something like, say, 5, 2, 2, 0. Okay, it's a symmetric matrix and it gives you the status of the curvature at this point. Remember, if you have just a line, then the curvature is just one number. For example, +5 or -5 or 0. 0 in case you don't have any curvature. That's if you have a line. If you have a line in the three-dimensional space, then the curvature is just 3 numbers like 5, 6, 2. And if you have a surface embedded in a three-dimensional space, then the curvature is a 2x2 matrix. Now, before I wrap up this video, let me just write the definition of the curvature tensor B in a formal way, in an explicit way. Let's put it that way. Beta alpha beta, it equals to the covariant derivative of the covariant basis, that is S alpha, dotted with the normal vector. You may be wondering, how did I get this from this? It is simple. I just dotted both sides with n. You know, it's just like the way I got the explicit definition for this from this. I dotted both sides with the contravariant version of, with the covariant version of this one. Okay, so zk.zk, the result is 1, and zk on the other side appears here. So it's very similar here. I just dotted both sides with the contravariant version of this n, and this was the result. So this is an explicit version, explicit formula for calculating the curvature tensor, that is B. And since it's a tensor, you can juggle the indices, so you can have B alpha alpha, that is the mean curvature tensor. You can have B alpha beta, B what? You know, everything you need. B beta alpha or anything. By the way, it's symmetric, so B alpha beta is equal to B beta alpha. Same thing. Okay, now finally, my last trick in this video. Remember when I told you that the difference vector cannot be satisfactorily represented by those two bases? Well, that's right, but what if we added to our toolbox another vector, that is the normal vector? This is n, and it can be unit normal vector. It can be easily calculated by doing a cross product between S1 and S2. Okay, that's a cross product. Then normalize it in order to ensure that this has a length of 1. So that's S1 cross S2, the norm. Okay, so we calculated the normal. Now we have a powerful toolbox that will enable us to represent any vector that belongs to the entire space, right? So why don't we just represent this vector using the 3 of those vectors? Well, we can do that, and guess what? We already did it. Yeah, believe it or not. And to be more precise, we already went through 66.6% of the way, 2/3 of the way. Because remember, we already projected the difference vector onto this plane. That is, we find those two components, S1 and S2. They are encoded here. And the only thing that we need to do now is to find the dot product between this vector and the normal in order to complete our representation of the difference vector using those 3 basis elements. Well, guess what? We already did it again. Yeah, it's the other side of the equation. This is the dot product between the normal and the difference vector, because if you moved this term to the other side, it will have a plus sign. And thus you will have 3 terms that are the 3 components multiplied by 3 basis vectors, those 3 basis vectors. And the result is the difference vector. In other words, what I'm saying is that the covariant derivative, the covariant basis, is simply the dot product between the rate of change of the basis with respect to each of these spatial variables dotted with the normal vector in order to get the component, and then dotted with the normal vector again. And that's why I said that this is equal to the normal vector times some scalar values. Yeah, and that this is the normal vector times some scalar values. In other words, we have another definition for if this is n and this is n, then we have another definition for the curvature tensor B alpha beta. We're saying that B alpha beta is equal to n, the normal vector, dotted with the rate of change of the covariant basis with respect to each of the spatial variables. And this is not contradicting this definition, okay? In this definition, we are saying that it is actually the normal dotted with the covariant derivative of the covariant basis. But when you remember that the covariant derivative of the covariant basis is composed of 2 terms, one of them is completely orthogonal to this n, so it will produce 0. So it's just about doing a dot product between this one and this one, as we can see here. So that brings us to the end of the video. Thank you so much for watching. And if you do have any questions, I will answer them, considering that the audience of this video is very small. So I will definitely have enough time to answer your questions. Thanks again and see you later.